Welcome to this presentation on digital signals and systems. The outline for this presentation is given here. We will briefly explain digital signals, the noise margins in TTL family, and then the reasons why we would want to implement our controllers as digital systems. Digital signals are the basis of digital systems. What are digital signals? They are quantized in value. They take the value 0 or 1, and they are also discrete in time. We shall often call digital signal as a discrete time signal in this course. The reason is that we shall not study the quantization effect in this course. For example, because of this, we will call digital signal as a discrete time signal in this course. Binary numbers 0 and 1 are used to represent digital signals. Now, 0 or 1 can be made to refer to a range of voltages. So, digital signals can be made less noisy. We will see this shortly. Basically, if a transmitted signal is received exactly, there is no noise. That is possible in a digital system. But the analog circuitry always has noise. Digital devices have good noise margins. We shall explain this with the transistor-transistor logic or TTL, which works with the voltage range 0 to 5. Okay, let's look at the noise margin at the low state. At low state, we expect the value to be somewhere close to 0. We want it to be as close as possible to 0. Because of the noise, the voltage can go up. So let's see some definitions in TTL. Let us consider a source device, and it generates a voltage, and this will go as an input to some other device. Okay, and this is at low level. The voltage here is considered low if the voltage here is less than 0.4 volts. All devices that obey the TTL standards will guarantee to provide a voltage below 0.4 volts at the low level, which means a TTL device could actually produce a voltage lower than this value. It could be 0.3 volts, 0.2 volts, and so on. In any case, it will be less than 0.4 volts. And that will be recognized at the input of another device as low, so long as it is below 0.8 volts, which means that this can actually pick up as it travels a voltage of up to 0.4 volts. It may actually be greater than 0.4. For example, it may be 0.2 here, whereas it can go up to 0.8. So in this case, it can go up to 0.8. It can pick up by up to 0.6 volts. But the guaranteed value is 0.4 volts. If it comes down, there is no problem. Suppose the voltage here is 0.3, and because of the voltage drop, it becomes 0.2 or 0.1. It's perfectly okay. It will still be low. Notice that it cannot go below 0 because TTL works in the range 0 to 5. So the guaranteed noise margin is 0.8 minus 0.4, and that is 0.4 volts at the low state. What happens at the high state? High state means we are denoting it by 1. The undesirable effect of noise is to make the voltage to come down. Let's see some definitions. Here it is considered high if it is greater than 2.4 volts. High level can go up to 5. But so long as it is above 2.4, it is considered high. It is considered high at the input so long as it is above 2 volts. In other words, this can actually lose up to 0.4 volts. The voltage can drop by 0.4 volts. In reality, of course, it could be a lot higher. For example, it could be 3.5 volts, in which case you have the margin of 1.5 volts. And at the high state, the undesirable effect of noise is to make the voltage drop. If it goes up, for example, to start with we have 3 volts, it goes to 4.5, that is goes up by 1.5 volts. It's perfectly okay. It will still be recognized as high voltage. So in other words, even if the voltage increases because of noise, you see that it will still be considered high here. So no problem if it goes up, only problem is if it comes down, and the guaranteed value is 0.4 volt at the high state 2. So in a digital device, even if the voltage changes as it travels from the output to the input, even if the voltage changes, it is still recognized as the same, as if nothing happened, and margins are provided to ensure this at the low state and also at the high state. So digital systems are based on digital signals. Noise margins can handle noise, drift, etc. Remember, such a protection is not available in analog systems. In addition, digital systems are easy to implement, it's easy to modify circuits, just change the coefficients. We can improve accuracy through more bits. We will see this in the next lecture. We can implement error checking protocols. We can produce digital devices in volumes. We can fully integrate them through VLSI. Of course, through a multiplexer, a single system can be made to handle a large number of digital signals. So digital systems became popular. This is the impetus for advancement of digital systems. Lately, the digital systems have become rugged, compact, flexible, and inexpensive. Modern devices are all digital. We expect the control algorithms to be derived in this course to be implemented through digital systems. We will often refer to digital system as a discrete time system in this course. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.